Now we're going to pull a lot of the things we've looked at together to try to go ahead and sketch the graph of a function using all of the pieces of information we now have at our disposal. So if we want to sketch a curve, the first thing we need to know is the domain. So we want to find the domain of the function. This will tell us about where we have vertical asymptotes, as well as some places that could or could not be local mins or maxes. Then from the first derivative, we want to be able to find where the function is increasing and decreasing. This can also help us find local mins and maxes. From the second derivative, we'd like to be able to determine where we are concave up and concave down, and also be able to determine inflection points. We also want to make sure we have all of the vertical and horizontal asymptotes of our function, and then to plot, we will draw in our asymptotes, plot local mins, maxes, and inflection points, and then use this information to sketch what's going on with the graph. So we're going to start off with this example where we're going to go through the entire process. In some of the later examples, you're just going to see us take the information we know and then sketch. But here we're going to go through the entire process again, just as a little bit of a refresher for everyone. So say we've got the function f of x equals 1 over x squared minus x. So this will be the exact same as x squared minus 1 to the negative 1. We want to know the domain of our function. So here we can't let x squared minus 1 equal 0, which tells us that x squared cannot equal 1, which tells us then that x cannot equal plus or minus 1. So that means that our domain will be negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Now say we wanted to go ahead and determine where we are increasing and decreasing to find our local mins and maxes. What we need to do is we need to go ahead and figure out what the derivative of this function is. But right now we have something where we're going to want to use the chain rule. So it'll be up to us to determine what the outside and inside functions are. Well, our outside function will be x to the negative 1, and our inside function will be x squared minus 1. The derivative of our outside will be negative x to the negative 2, and the derivative of our inside will just be 2x. So then the derivative will be negative x squared minus 1 to the negative 1, to the negative 2 times 2x, which can also be rewritten as pencil is not cooperating. Close enough. Which is the same thing as negative 2x over x squared minus 1 squared. Now, if we want to be able to look at where we're increasing and decreasing, we need to find our critical points. So this was how we did the chain rule. And so we want to be able to find the critical points. In order to find those, we need to go ahead and set the derivative equal to 0 for one of the options. So this would be negative 2x over x squared minus 1 squared equals 0. If we multiply this over, we're just going to end up getting that negative 2x equals 0, which would tell us that x equals 0 is going to be one of those critical points. We also want to look at where the derivative does not exist and what values we might have that could cause other critical points to happen. And if we notice here at the denominator, we're going to have a very similar issue that we had before, where x cannot equal positive or negative 1, or rather, when x equals plus or minus 1, those are the places where the derivative does not exist. But notice that these aren't in the domain anyway. So they're not critical points. Alright. We also then want to take a moment to break up our interval that we're looking at based on the issues in our domain and with our critical points. So we know that 0 is a critical point, and we know that negative 1 and 1 are problem points. So 0 is a place we have to look at, negative 1 is a place we have to look at, 1 is a place we have to look at, and we have to look at places in between these intervals. So we just need value below negative 1, above 1, between negative 1 and 0, and between 0 and 1. So you don't have to choose the same values I do that I'm choosing in red. I'm going to choose negative 2 and 2 for being outside of these, on these outside intervals, and I'm going to choose negative 1/2 and 1/2 to determine where we're at on these other intervals. So again, we're looking at the sign of the derivative, and that will tell us about where our function is going up versus going down. So we want f prime of negative 2, f prime of negative 1/2, f prime of 2, and f prime of positive 1/2. So again, our derivative is this negative 2x divided by x squared minus 1 squared. Apparently my batteries are low and my calculator recommends a change of them. So if we want to go ahead and plug this in, we'll get in the numerator negative 2 times, this will be our x, negative 2, divided by negative 2 squared minus 1 squared. And if we did all of that correctly, we should get 0.4 repeating. But fortunately, the big thing we need to worry about is that that's positive. If we plug in a positive 2, into our function, we'll get a negative 0.4 repeating, which is negative. So far what we know is that we've got a negative value when we are greater than 2. So this will be negative, which means our function's going down. And over here, when we're around negative 2, our function's actually increasing. So that's something for us to keep in mind. We also want to know then what's going on when our function our derivative has negative 1/2 and positive 1/2 plugged in. So we plug in negative 1/2 first, negative 1/2. We end up with positive 1.7 repeating, which is positive, which means we are increasing here. And if we plug in a positive 1/2, we get negative 1.7 repeating, which again is negative. So our only critical point was 0, and it looks as though we're going up when we are approaching 0 and down when we're leaving 0. So this is going to be a local max because we're going up and then down. So local max at the point 0, f of 0. And so if we want to know what f of 0 is, all we have to do is plug in 0 to our original function. So that would be 0 minus 1 which will be 1 over 0 minus 1, which will be negative 1. So we get the point 0, negative 1 as a local max. This also tells us that that f is increasing on negative infinity to negative 1 and negative 1 to 0, and it is decreasing on 0 to 1 and 1 to infinity. So some things we can use later on to help us graph. Alright, after this we're going to go ahead and move on to our inflection points and determining the intervals of concavity. In order to do this, we need the second derivative of this function. So if we want to find the second derivative, we want the derivative of this. So just as a little bit of a reminder for ourselves, this would be negative 2x times x squared minus 1 to the negative 2. We also could just at that point go ahead and do quotient rule if we wanted to. So there's multiple paths here that we can take in order to take the derivative of this function, whether it is you want to use the product rule or the quotient rule. We will, of course, need to use the chain rule a little bit in here. I will leave this one for practice, but I will tell you what the derivative is. The derivative here, which is the second derivative overall, will be 6x squared plus 2 over x squared minus 1 cubed. And again, I encourage you to try to find this derivative on your own. And if you're having trouble getting this derivative, talk about it in the discussion board. Figure out why it is that your approach maybe isn't quite getting what you need to. Now, if we want to find where these potential inflection points are and figure out where we need to look at for our domain, we either need to look at where the second derivative equals 0 or where the second derivative does not exist. We'll talk about does not exist first because it's easier. Here, we just know it does not exist when x is positive or negative 1. But again, as we discussed before, this is not in the domain anyway. Now, if we look at where the second derivative equals 0, what we're saying is 6x squared plus 2 over x squared minus 1 quantity cubed equals 0. Multiplying the denominator over, this tells us that we have 6x squared plus 2 equals 0. In order for that to be true, we would need 6x squared to equal negative 2, which means we would need x squared to equal negative 2/6 or negative 1/3. It doesn't matter what we call it though, because x squared can never be negative, so this has no solutions. So at the end of the day, there's no possible inflection points. So when we looked, we couldn't get the second derivative equal to 0, and the places where we're able to make the second derivative not exist, those were already on our domain to begin with. But that doesn't mean we don't want to know where we're concave up and concave down. So with that in mind, we'll go ahead and again break up our interval based on some of the things we know. We know where our issues in our domain are, and that's really all we need to be worried about, is where that domain gets broken up. Those are the places where we can change with concave up and concave down. Again, we want to look at the sign of our second derivative to tell us about what's going on with our function. So we'll plug in some points. -2, 0, and 2 are the points I'm going to choose. Again, you're allowed to pick any number you want, in this case between -infinity and -1, not including those. Between -1 and 1, again not including those, and between 1 and infinity, not including those. I've picked -2, 0, and 2 because I think they're numbers that are easy to work with. So we should plug into our second derivative here, and our second derivative is 6x, which if we plug in -2 first, will be -2 squared plus 2 divided by -2 squared minus 1, all raised to the third power. So the important thing here is that second derivative at -2 is positive. So that means we are concave up. I'm going to go ahead and plug in +2. So that will require me to delete the fewest number of things. That will again be positive. And if we want to check where the second derivative equals 0, so on that middle interval, this actually ends up being negative. So this was positive, so it's concave up on that interval, and this is negative, so we're concave down on this interval. So we are, I'll write the summary in blue, f is concave up, which remember we're using this symbol on the interval -infinity to -1, and on the interval 1 to infinity, and f is concave down, which is this symbol on the interval -1 to 1. Alright, so next we want to find our asymptotes. So we want to go ahead and figure out where the horizontal and vertical asymptotes are going to be. For the horizontal, what we need to know is what the behavior looks like when the limit as x approaches infinity of our function, and what the behavior is when the limit of x is approaching -infinity of our function. So remember, we're talking about the original function here, which means we want the limit as x approaches infinity of 1 over x squared minus 1. So again, we can break this down by dividing the numerator and the denominator by 1 over x squared. This will be the limit as x approaches infinity of 1 over x squared divided by 1 minus 1 over x squared. Or we can remember our rule that since we have a larger power of x in the denominator, this is going to go to 0. Same thing here, we'll have the limit as x approaches -infinity of 1 over x squared. And again, by our rules, this will be 0 as well. So we have a horizontal asymptote at y equals 0. So take that information and we'll run with it. As far as our vertical asymptotes go, this is where the denominator of the function is 0 as long as f is simplified. So if we have something where we could algebraically remove that discontinuity, then it would be something where we would not have an asymptote there. So we saw that much earlier on. There were some discontinuities that we could remove, removable ones, and there were others that were infinite discontinuities. In this case, we're looking at x is plus or minus 1. So there was no way to remove either of those discontinuities, so we're stuck with what we got. Alright, now what we'd like to do is we'd like to take all this information to sketch the graph. So some things we can write down from the get-go. We know what our asymptotes are, so we know that x equals 1 and x equals negative 1 are both going to be vertical asymptotes. We also know that y equals 0 is going to be a horizontal asymptote. Now, if there are any points that we have, we should plug those in. We didn't have any inflection points, but we do know that this point 0, negative 1 is a local max. When we take our information we know about the first and second derivatives, we know that the first derivative is going to only have things to be concerned with where we have our critical point and where we have our discontinuities, where we have these vertical asymptotes. So it is increasing during this entire time. Increasing here, and decreasing here. We also know for the second derivative that we don't have any inflection points, and all we need to worry about are these discontinuities. And we are concave up until we get to negative 1, then we are concave down, then we're back to concave up again. And we can use all of this and our limits as we're approaching negative infinity and infinity to sketch what our graph is. So we know between negative 1 and 1 we have a local max. And we know that we're concave down. So we should have something where our function is increasing, and we have kind of this curve downward as we do this. And then once we hit this point, we go back to decreasing. When we're over here, we're going to be increasing the entire time, and our curve should go like this so that we're concave up. We also know that we should be approaching infinity then at this point. And we know that our limit as x approaches negative infinity equals 0. We also know that our limit as x approaches positive infinity of our function equals 0. So here we're going to start off very high and we're going to be decreasing the entire time as we get closer and closer to 0. So this in the blue ends up being our function. The red helps us determine where our asymptotes are and kind of helps us get the general shape of the graph. Now for the next two examples, we're going to pretend that we had gone through all of this process that we had just done. It's a long process. It takes basically the entire course up until this point worth of things to wrap our head around, right? We need to know limits, we need to know derivatives, we need to know how to find vertical and horizontal asymptotes, we need to know how to find intervals of increasing, decreasing, mins and maxes, concavity, inflection points. It's a nightmare. It's not a lot of fun. The point of this section, though, is to explain how we combine those things. So we've learned how to do all of those other things at this point. And so the question will be, if we have them, how do we make the graph? So in this example, we're going to attempt to sketch the graph of our function with these properties. We know f of x equals 0 at x equals 1. So this is the point 1, 0. So x is 1, the function value is 0. F prime of 1 is 0, and f double prime of 1 equals 0. So this tells us, if we know that the first derivative at this point is 0, that we have a horizontal tangent at x equals 1. So it could be something where it's a min or a max. So could have min or max at x equals 1, and there may be an inflection point. At x equals 1. So again, at the moment we don't know. These are things that are possibilities right now. We're told that the limit as x approaches 0 of f of x is infinity, and the limit as x approaches 2 of f of x is negative infinity. So these tell us, since we're going to infinity or negative infinity with these are vertical asymptotes. Of x equals 0 and x equals 2. We know that our derivative is positive when x is less than 0 and x is greater than 2. So this is saying that we are increasing on negative infinity to 0 and to infinity, but decreasing otherwise. So we're decreasing on the interval 0 to 1 and 1 to 2. So when x is between 0 and 1, and when x is between 1 and 2. We also know that our second derivative is less than 0 when x is between 1 and 2, and when x is greater than 2. So concave down on 1 to 2 and 2 to infinity. Last but not least, we know that the limit as x approaches infinity of f of x is 1, and the limit as x approaches infinity of, or negative infinity of f of x is 0. So these are horizontal asymptotes of y equals 0 and y equals 1. So this is a lot of information to kind of take in at once. But what we want to do is we want to try to break down what we know about the first and the second derivative. We don't have all the information, but it should be enough to make a good guess. So for the first derivative, we know that we're worried about 0, and we're worried about 2, and we know we're worried about 1. So these are where our vertical asymptotes happens, which is why we're worried about those. And we're worried about 1 because we were told that it could be a place where you have a min or a max, or it could be a place where there's an inflection point. We don't know yet. But we know that we're increasing on negative infinity to 0. So when we are on this interval, we are going up. We're positive, so we're increasing. So this is f prime, this is f. And when we are between, we're also increasing on 2 to infinity. So this is positive, this is increasing. We're also decreasing on 0 to 1 and 1 to 2. So we're negative here and negative here, so we're going down, and we're going down again. So we kind of are going down, we stop at some point, and we continue to decrease. So this, because of what we know here, is neither a min nor max. So it's a contender, but in the end we don't have one. For the second derivative, again, the places we care about are 0, 1, and 2. And we know we care about 0 and 2 because these are the places where we have vertical asymptotes. And we know we care about 1 because we were told that the second derivative equals 0 at that point. So it's a potential critical point. So we're told that the second derivative is less than 0 on 1 to 2 and 2 to infinity. So in both of these instances, it'll be concave down. Now what we're not told is what's happening to the second derivative over here. I might have accidentally deleted that line, might be left out for some reason, but we're not able to say whether or not it's a critical point unless we know more about the derivative there. So if we did happen to say that the second derivative was greater than 0, then we'd be able to maybe say some things about what's going on over here. But right now, we're not sure. So if I said for h, f double prime of x is greater than 0 when x is less than 0 and x is between 0 and 1, then we'd have enough information to be able to say this is positive, and so we are concave up in those places. So let's work with that assumption. Let's go with that. So that means that this is an inflection point. And we know that the point there is 1, 0. So again, let's take what we know. We know that we have our tangent lines. So we'll graph those first. Or sorry, not our tangent lines, our asymptotes. So we'll have vertical asymptotes at x equals 0 and x equals 2. So that will go here. And here. We also know that we have horizontal asymptotes at y equals 0 and at y equals 1. Again, we're allowed to cross these horizontal asymptotes, but we'll need them when we're trying to describe our end behavior a little bit later. We know also that we have this point 1, 0 that is an inflection point. And then we can use these intervals of going up and down, talk about f prime and f double prime. So f prime is positive here, negative here, and positive here. And f double prime is concave up, concave down, and concave down on those places. So when we're over here, we know that our limit as, we can't see that, our limit as x approaches negative infinity is 0. So starting from here, infinity of the function is 0. So we're going to start as close to 0 as we can. And we know that as we continue on, we are going to be increasing, and we're going to be going toward infinity, and we're going to be concave up. Now we know that we're going towards a positive infinity, 1 because we're increasing, 2 because we're concave up, but 3 we said specifically that our limit as x approaches 0 was infinity. So on both sides we are going up. coming from infinity. So we will look at something like this, where we are going up slowly but surely, and then we shoot up towards infinity. When we get to the other side of 0, we're going to be coming down because we're decreasing. We'll be coming from infinity because that's what our limit said. And we'll be concave up, so we should curve in this direction as we approach the inflection point. Now once we get to this inflection point, we're going to continue to decrease, but now we're going to be curving the other way. So curving concave down. And again, we know that we should be going towards negative infinity here. 1, because we're decreasing, but 2, because we're told that the limit as x approaches 2 of the function is negative infinity. So we'll go down to negative infinity, and on the other side we'll be coming up from negative infinity. We know that we're coming up because we're increasing, and we should be concave down. And one other thing to remember is that the limit as x approached infinity of the function was equal to 1. So we want to be going towards this other horizontal asymptote as we finish things off. So this is a sketch of what our function should look like. We'll go through one more example. Say we want to sketch the graph that has these properties. So we're going to say that the first derivative is 0 only when x is 0 and x is 8. So we know we have horizontal tangent lines at x equals 0 and x equals 8. These are possible mins or maxes. We know that our second derivative equals 0 when x is 0, and it equals 0 when x is 10. So we have possible inflection points at x equals 0 and x equals 10. We know that our function equals 0 at -5, -2, and 6 on the x-axis. So we have points -5, 0, -2, 0, and 6, 0. Our first derivative is greater than or equal to 0 when x is between -4 and 4, and when it's between 4 and 8. So it is increasing on -4 to 4 and 4 to 8. Not sideways 8, just regular 8. We know that it is less than or equal to 0 when x is less than 4, so -infinity to 4, and when x is greater than 8, so 8 to infinity. We also know that the second derivative is greater than 0 when x is between 0 and 4, and when it's greater than 10. So it's going to be concave up on 0 to 4 and 10 to infinity. It has 2 vertical asymptotes, and these are at x equals -4 and x equals 4. And the limit as x approaches infinity of the function is 3. So that tells us that we have a horizontal asymptote at y equals 3. And this applies to the right because it's talking about positive infinity. So what are some things that we know? Well, we know about the first derivative. The first derivative is going to have a number of places we have to look at. We have to look at -4. We have to look at 0. We have to look at 4. And we have to look at 8. So why did we pick these? Well, we know that there are horizontal tangent lines at 0 and 8. So those are places where we could have mins or maxes. Those are going to be some of our critical points. We also know that the derivative, that we have vertical asymptotes at x equals -4 and x equals 4. So again, these are places in our domain we'll need to worry about. So again, we can pick some things we know. We know that we are increasing on -4 to 4. So that means we are going up here and up here, even though we know that the derivative here is 0. That means this is not going to be a min or max. We also know that when we're going from 4 to 8, we are increasing. So all of these places we are going up. We're decreasing on -infinity to -4. And we are decreasing from 8 to infinity. So we are decreasing here. Since we have to go up and then go down to get to 8, where we know the derivative equals 0, we have a local max at x equals 8. We don't actually know the function value, so we're only going to just plug something in and guess. So again, at the moment we're just sketching the curve. If we don't have the information, then there's nothing we can do. And we know about our concavity only on 0 to 4 and 10 to infinity. So that tells us that we're concave up. We might assume we're concave down otherwise, but it's hard to say for sure. So let's then sketch. We know that we have vertical asymptotes at x equals -4 and x equals +4. And we know we have a horizontal asymptote of y equals 3. We're told about a few of our points. So we know we have a max, but we don't know what the function value is. But we do know that we have -5, 0 as a point. We know that we have -2, 0 as a point. And we know that we have 6, 0 as a point. So all of these need to be points that we are considering. We also know that we have some horizontal tangent lines whenever x is 0 and when x is 8. So we're not quite sure where those are going to end up being yet, but there's some things for us to keep in mind. Kind of keep what's going on with our derivatives in the back of our mind as well. We know that we are decreasing here, increasing here. We know that we've got a horizontal tangent line here to worry about. We know that we then go right back up to increasing. We're increasing again when we get to the other side of this asymptote, and then when we get to 8, we are decreasing. We know for our second derivative, not a lot, but we do know that between 0 and 4, we're concave up, and we know that between 10 and infinity, we are also concave up. So we know we're decreasing on this part, and we don't actually have a left asymptote to worry about. We don't have to worry about what the end behavior is on the left, so we're going to say it's coming down from negative infinity. And all we know is that we are decreasing on this part. So we can guess that maybe we're concave down, but we don't have the information available to us to say for sure. When we get back on the other side of that asymptote, we will be increasing right up until we hit 0. At 0, we actually stop increasing for a second. We have a horizontal tangent line right here. Or sorry, nope, not yet. Let me back up for a second. We know we had to go through this point over here of negative 5, 0. We also know that we have to go through this point of negative 2, 0. And we're not sure what's going on when we get to x equals 0, but we do know that wherever we're at, there should be a horizontal tangent line. I'm going to denote that with HTL. Now from here, it's going to go back up to increasing, and it'll be concave up during this time. So we know that we should have something that looks like this when we get to the other side of our horizontal tangent line. When we come here, we're again going to be going up, but in order for us to be going up, we have to be coming from somewhere. So we're going to be coming from negative infinity. We need to go up until we get to this 0.60. We'll again be going up in order to hit our max. And once we hit our max, we're going to be going down. Now it's not clear how long we're going to be going down, but once we hit 10, we're going to have to be concave up. So we should make sure that that part ends up being concave up at that point. And we know that the limit as x approaches infinity of the function is going to be 3. So that means that we're continuing towards this y equals 3 as we keep going. Now again, some things we didn't have. We didn't know what this point was. We knew there had to be a horizontal tangent there. We didn't know necessarily if we were going from negative infinity to infinity, but we could assume some things based on if we had to be increasing or decreasing when we got to certain points. We didn't know what this point was, and the only reason we even would guess to put it above the line is if after this we have to be decreasing and somehow get to 3, we need to be above 3 in order to decrease to get there. So in general, we're going to have more information than this. We should have the original function to be able to determine all the different pieces, but this helps us get the idea of how we can go ahead and sketch a curve even if we don't know everything.